In 1900, Lord Kelvin gave a speech that physicists would quote for the next 120 years, mostly as a warning. Over the beauty and clearness of the theory, he said, there hover only two small clouds. Within 5 years, one cloud had grown into the theory of relativity, the other into quantum mechanics. Two small clouds rebuilt all of physics. This is the puzzle at the heart of how physics gets passed from one mind to another. Not the physics of textbooks, not the physics of science fiction, but real physics, the kind that takes a decade to learn and another decade to use. The kind where the question isn't how to explain an answer, but whether the right question has even been asked yet. Let's start somewhere ordinary. You are 12 years old, and someone hands you a thin paperback about the universe. The title promises to explain everything. Stars, black holes, the beginning of time. You read it in an afternoon. You understand most of it, or at least you think you do. The words are familiar. The ideas feel profound. You close the book feeling like you have touched something enormous. Now you're 18. You have passed your entrance exams. You arrive at the physics department. Someone hands you a textbook. The words are different now, precise, careful, stripped of color. You read it in a week and understand almost none of it. The feeling of touching something enormous is gone. In its place is the feeling of standing outside a locked door, listening to sounds you cannot interpret. What happened between those two moments? Not stupidity, not a failure of the books. Something much more interesting and much more troubling. There is a strange geography to popular science. Most people imagine it as a single ladder. You start at the bottom with the simplest books, and you climb. Each rung brings you closer to the real thing. And one day, if you climb long enough, you arrive. But that is not how it works. The landscape of popular science is not a ladder. It is more like a city with many separate buildings, and the buildings do not share entrances. You can live your entire life in one building without ever visiting the others. There are books that explain the beauty of physics to people who will never do physics. There are books that inspire a kind of awe, a sense of the universe's strangeness, without actually teaching you to navigate it. These are not lesser books. They serve a genuine function. They are cathedrals. Magnificent, moving, and not particularly useful for building more cathedrals. And then there are the other books, the ones that assume you remember your school mathematics, the ones that do not apologize for their difficulty, the ones that live in a different building entirely, connected to the cathedral by no obvious walkway. These books are not trying to fill you with wonder. They are trying to give you tools. The difference is enormous, and almost no one talks about it. The physicist who sits down to write one of these rarer books faces a problem that cathedral builders never have to confront. Every place where a formula would clarify, you must find words. Every place where an equation would take 3 seconds, you need half a page. And not just any words. Careful words, accurate words. Words that do not accidentally simplify the thing into something false. Because a formula, strange as it sounds, is a kind of mercy. It says exactly what it means. A formula cannot lie. It cannot create the comfortable illusion of understanding. You either follow it or you do not. Words are different. Words are seductive. You can read a paragraph about quantum mechanics and feel, for a vivid moment, that you have understood it. The feeling is indistinguishable from actual understanding. This is the great danger of popular science, and almost no one warns you about it. There is a famous story, perhaps apocryphal, like all the best stories in physics, about two physicists meeting at a conference. One has written a book explaining the other's most celebrated result. The author gives the book as a gift. The physicist flips through it, pauses, and says, "But this is not quite right." The author says, "I know, but it is as close as you can get without the mathematics." The physicist thinks for a moment, then says, "And perhaps that is close enough. Perhaps it is. But close enough for what? This is the question that matters. Close enough to feel the weight of the idea? Yes, absolutely. Close enough to actually use it? No. And there is nothing wrong with this as long as everyone is honest about it. The problem is when the two get confused. When people believe that because they have read the book, they understand the physics. When the feeling of understanding gets mistaken for understanding itself. The honest books, the ones that insist on formulas, that admit when words are insufficient, that do not pretend to explain more than they can, these books serve a different reader. They serve the reader who suspects that the feeling of understanding is not enough. The reader who wants to be able to calculate something, to predict something, to be wrong in a way that can be corrected. This reader is rarer, but they exist, and without good books written specifically for them, they end up stranded between the cathedral and the technical literature with nowhere to go. Who exactly is this reader? Not the person who has decided to become a physicist. They have textbooks. Not the person who loves the idea of physics, but has no intention of going deeper. They have the cathedrals. This is the person in between. The engineering student who took an abbreviated course on relativity and suspects there is more. The programmer who understands mathematics well enough to follow an argument if someone bothers to make it. The doctor who remembered, when she was 17, how much she loved the strangeness of quantum mechanics, and who has kept that love alive through 2 decades of other work. And, perhaps most importantly, the high school student who is clearly going somewhere in mathematics or physics or chemistry, who has been reading the simple books and finding them increasingly insufficient, who is starting to suspect that the gap between what they know and what they need to know is wider than anyone has told them. This student exists in large numbers, and the books written for them are startlingly rare. Think about what it means to build a bridge for this reader. You cannot pretend that formulas do not exist. They exist. They are, in fact, the point. But you also cannot simply write equations and call it popularization. You have to find the middle path. The path that Feynman walked better than anyone who has ever lived, and that almost no one else has managed to walk at anything approaching his speed. Richard Feynman had a gift that is nearly impossible to fully describe, because part of it was simply his particular brain, and brains cannot be replicated. But the principle behind his gift can be stated. Feynman never let words and formulas become strangers to each other. In his lectures, a physical argument and a mathematical argument were the same argument, told in 2 different languages simultaneously. He would say a thing in words, really physical, intuitive, almost spatial words, and then he would say it again with symbols, and the 2 versions would illuminate each other. The word version told you what to expect. The formula version told you whether you were right. This is much harder to do than it sounds. Most physicists, when they write, choose a side. Either they commit to the verbal descriptive mode, putting the reader at ease, removing technical barriers, making physics feel accessible, or they commit to the formal mode, writing for the reader who already knows the territory. Very few physicists can genuinely operate in both registers simultaneously. Julian Schwinger, for example, operated almost entirely in the formal register. Schwinger was, in the estimation of many of his colleagues, a more technically accomplished physicist than Feynman. He did not become the household name that Feynman became, and this is precisely why. His writing was dense to the point of opacity. To follow a Schwinger paper, you had to essentially redo his calculations step by step. There was very little verbal guidance, very little of the physical intuition that Feynman scattered through everything he wrote. Schwinger's work needed an interpreter. It was complete, it was elegant, it was often brilliant, but it was a locked room. You needed someone to hand you the key. This distinction matters not just for popular science, but for physics itself. The way a physicist thinks, whether primarily in words and physical images, or primarily in symbols and formal structures, shapes what problems they can see and how they attack them. Werner Heisenberg wrote books of philosophy. Niels Bohr spent most of his conversations asking what people actually meant. Dirac was formal to an almost inhuman degree. These were not personality quirks. These were different instruments being played to get at the same underlying music. The music in this case is a set of three theories that between them describe almost everything a physicist needs to know to make technology work. Quantum mechanics, the theory of the very small, special relativity, the theory of the very fast, general relativity, the theory of the very heavy. These three frameworks, built mostly in the first half of the 20th century, are the foundation on which every semiconductor, every GPS satellite, every MRI machine stands. You might think that because they are so foundational, every engineer understands them. The uncomfortable truth is that most engineers understand fragments and approximations, carefully chosen fragments that happen to be sufficient for the engineering they need to do. The full theories live somewhere above, in a region that most people never visit. This is not ignorance on the engineer's part. It is rational specialization. If you are designing a bridge, you do not need to know why special relativity requires corrections to the GPS signals your survey equipment uses. You just need to know that the equipment works. But there is something lost in this arrangement. Something is lost when the full picture becomes the exclusive property of a small group of specialists, and everyone else works with calibrated fragments. The loss is not practical. It is something harder to quantify. It is the loss of the sense that the world holds together, that the fragments are pieces of one thing, that the strangeness you felt as a child reading about black holes is connected to the strangeness of why chemical bonds form the way they do, which is connected to the strangeness of why the GPS in your phone works at all. This coherence, the feeling that physics is not a collection of separate magic tricks, but a single, extraordinarily strange, unified story. This is what gets lost when the full theories are not explained to anyone except future specialists. And this is precisely what good popular science, at the harder end of the spectrum, is trying to restore. Not to teach people to do physics, not to give people the tools to calculate, but to give people back the coherence, to let them stand in a room and see dimly but unmistakably how the walls connect to the ceiling. The question of how physics actually progresses not in textbooks, but in reality, is one that most popular science gets badly wrong. The standard story goes something like this. A brilliant person has an insight, formulates a theory. The theory makes predictions, experiments confirm the predictions, the textbooks get rewritten. This is a story so clean and orderly that it could only be a myth. The reality is closer to controlled confusion. Physics does not move forward uniformly. It moves forward in bursts, along fronts that shift without warning. At any given moment, some corners of the field are alive with excitement. People are crowding in, papers are coming out faster than anyone can read them, conferences overflow, everyone has the feeling that something enormous is about to break open, and in other corners of the same field, it is quiet, not because the questions have been answered, but because nobody currently knows how to attack them. The way a theoretical physicist lives inside this landscape is difficult to explain to someone outside it. There is no experiment waiting for you. There is no apparatus to adjust, no sample to prepare, no data to clean. There is a problem, usually a problem that has been sitting there for years or decades, and there is mathematics, and there is the accumulated knowledge of other people who have tried and partially failed, and there is time. Mostly there is time. Research physics is not a sequence of bright moments interrupted by ordinary work. It is ordinary work, long stretches of ordinary work, interrupted occasionally, rarely, by moments of brightness. This is the single most important thing that popular science almost never conveys. The gap between the problem and the solution in real research is not a paragraph. It is not an evening of inspired thinking. It is months. It is sometimes years. During those months and years, very little happens that would be interesting to an outside observer. You read. You calculate. You find that the calculation does not say what you hoped it would say. You try a different approach. You read more. You talk to people. The conversation leads you sideways towards something you were not looking for, and that sideways thing turns out to be useful, or it turns out to be a dead end. You will not know for a while. This has important consequences for education. consequences that are almost never discussed. The skills that research physics rewards are not the skills that most educational systems develop. Research rewards the ability to sit with a problem that does not yield. It rewards comfort with not knowing. It rewards the capacity to stay interested in something for a year without the regular reinforcement of a correct answer. It rewards tolerance for failure that looks, from inside the failure, completely indistinguishable from progress. The skills that most educational systems develop are roughly the opposite. Education rewards the rapid solution of well-posed problems. It rewards performance under time pressure. It rewards the ability to retrieve and apply known methods. It rewards, ultimately, the ability to be correctly measured. These are real skills. They are useful, but they are not the skills of research. The sharpest version of this disconnect shows up in a phenomenon that every physics educator has noticed, usually with a mixture of admiration and concern. The Olympiad student. The Olympiad student is, by any conventional measure, extraordinary. They solve in minutes problems that take ordinary students hours. Their mathematical reflexes are finely tuned. Their pattern recognition is extraordinary. They have been training for years to do exactly what they do, and they do it beautifully. And then many of them, when they arrive at research, stall. Not all of them, there are exceptions, as with every generalization, but enough of them stall that the pattern is impossible to ignore. Something goes wrong in the transition from the competition environment to the research environment, and the something that goes wrong is structural, not personal. Competition problems are solved quickly. Research problems are not solved quickly. Competition problems have known solutions. Research problems may or may not have solutions, and you will not know which until after you have found one or confirmed that you cannot. Competition problems reward speed, elegance, and the rapid identification of the correct method. Research problems reward exactly the opposite. The willingness to try the wrong method for a long time before finding the right one, if a right one exists. The Olympiad student who has spent their entire educational life being rewarded for speed, for the rapid solution, for the clean performance, this student has often developed a relationship with difficulty that is the exact inverse of what research requires. They have learned that if a problem does not yield quickly, the right response is to try a different approach immediately. But in research, if a problem does not yield quickly, the right response is usually to stay with it, to go deeper into the difficulty, not sideways around it. There is also a more subtle psychological issue. Olympiad students are, almost by definition, accustomed to success. They have been succeeding, visibly and measurably, and in competition with others, for years. Research does not offer this. Research offers long periods during which you are not sure whether what you are doing is working, followed by occasional moments of clarity. The student who needs the regular confirmation of a high score, a prize, a ranking, this student may find research nearly intolerable, no matter how intelligent they are. This is not a criticism of Olympiad students. It is a description of a mismatch. The mismatch exists because we have built educational systems that are very good at identifying certain kinds of ability and not very good at identifying other kinds, the kind of ability that research requires, the ability to sit with uncertainty, to sustain effort without external confirmation, to be genuinely curious about a problem rather than eager to close it. This kind of ability is almost invisible to conventional measurement. It does not show up on timed exams. It does not produce dramatic performances. It grows slowly in people who have been given space to be confused without being penalized for their confusion. There is a correlation that experienced physics educators notice and rarely know quite what to do with. Students who come from smaller cities, from less prestigious schools, from educational environments that were less intensive and less relentlessly optimized, these students often outperform in the research setting students who come from elite schools in major cities. Not universally, not without exceptions, but often enough that the pattern deserves attention. The explanation is not that the elite schools produce worse students. The elite school students are often measurably better prepared. They know more. They have practiced more. Their technique is more refined. But preparation and motivation are not the same thing. And there is something that happens to students who are subjected to too much preparation, too early, too intensely, for too long. Something in them gets used up. By the time they arrive at university, the question they are trying to answer is no longer what is true or how does the world work. The question has become, how do I perform well enough? The two questions are not compatible. The first one leads to physics. The second one leads to performance. The student who arrives from a less intense background has often not had this switch flipped. They are still asking the first question. The physics is still real to them, not an instrument for achieving scores, but an actual description of an actual world that is actually strange and actually worth understanding. This student may be slower to solve problems. They may have gaps in their preparation, but they have preserved something that the elite school student has sometimes had educated out of them. The desire to know. This matters for how we think about education, but it also matters for something larger. It matters for what we believe physics is for. If physics is primarily a competitive achievement, a set of performances to be assessed and ranked, then the Olympiad model is rational. You select for performance ability, you optimize for performance, and you celebrate the best performers. But if physics is primarily an investigation, a collective human attempt to understand the structure of reality, then performance ability is necessary but not sufficient, and the educational model that optimizes for it while ignoring everything else is doing something problematic. The collective nature of physics is something that popular science consistently underrepresents. The lone genius having a flash of insight in a dark room. This is the narrative that has attached itself to the history of physics because it is a good narrative, because it has human scale, because it can be told in a paragraph. The reality is that even the most solitary theoretical physicist is embedded in a dense network of conversations, collaborations, arguments, and accumulated knowledge without which their work would be impossible. Science is fundamentally social. Not in the soft sense that scientists are nice to each other, they are often not, but in the hard sense that the process of inquiry requires other people. You cannot evaluate your own work. You cannot see your own assumptions. You cannot identify the point at which your reasoning goes wrong, because the reasoning that takes you wrong is the same reasoning you are using to check whether you went wrong. You need someone else. Not necessarily a collaborator. Not necessarily a friend, but someone who will push back, ask what you mean, tell you that the thing you thought was obvious is not obvious to them. This is why the tradition of the scientific school matters so much, and why its gradual erosion is something to take seriously. The scientific school is not a building or a curriculum. It is a set of people who share a way of thinking, a set of problems, a history of conversations. The person at the center of such a school carries in their head the accumulated knowledge of all those conversations, and they transmit it not primarily through lectures or papers, but through the daily work of asking questions and insisting on clarity, through the 30-year-old habit of not letting an answer go until it is actually an answer, through the willingness to tell a student that what they said sounded good but doesn't actually mean anything. This transmission cannot be institutionalized. It cannot be standardized. It does not show up in any evaluation metric that a government ministry would recognize. And this is precisely what makes it vulnerable, not to malice necessarily, but to indifference. Systems that are optimized for measurable outcomes tend, over time, to crowd out the things that cannot be measured. The scientific school cannot be measured, so it gets crowded out. The physics community has watched this happen with varying degrees of alarm in different countries at different speeds. The pressure is always presented as rationalization, efficiency, accountability, transparency, the fair allocation of limited resources. And the pressure is not entirely without justification. Resources are limited. Accountability is legitimate. The question is not whether to have standards, but what the standards are measuring and what they are missing. What they tend to miss is exactly the thing that makes physics work: the long game. The decades spent on a problem that might yield nothing. The conversation that seems irrelevant and turns out, 3 years later, to be the key. The student who performs badly on every examination and does outstanding work in the lab. The senior researcher who would score poorly on any productivity metric, but whose questions keep everyone else honest. The physics community has its own internal trends and fashions, and these are driven partly by intellectual excitement and partly by funding patterns, and partly by the sociological dynamics of a relatively small community in which the enthusiasms of a few prominent people can redirect the work of hundreds. String theory, for a period of several decades, functioned as a kind of organizing principle for a large fraction of theoretical physics. It attracted enormous amounts of intellectual talent. It produced genuine mathematical advances. It also gradually drifted away from the possibility of experimental contact. It became increasingly difficult to say what experiment would confirm or refute the theory's central claims. This created an unusual situation, a theory that was mathematically rich and technically demanding, that occupied the attention of some of the most talented people in the field, was simultaneously a theory about which the question of experimental verification had become somewhat awkward to raise. The community's response to this situation was varied. Some people insisted that the experimental contact would come eventually and that the mathematical development was intrinsically valuable in the meantime. Others became skeptical of the theory's fundamental premises. Others migrated to adjacent areas, cosmology, which was becoming increasingly precise and increasingly capable of constraining theoretical options. Pure mathematics, which absorbed many string theoretic techniques and found them useful for entirely different purposes. What this episode illustrates is something about how science navigates uncertainty. When the experimental path forward is clear, when there is a measurable prediction waiting to be tested, the field has a kind of compass. Work proceeds, the compass points. You know whether you are getting warmer or colder. When the experimental path is unclear, the field has to navigate by other instruments. Mathematical beauty, internal consistency, the intuitions of experienced people about where the deep structure of the theory is pointing. These instruments are less reliable than experiment, but they are not worthless, and the history of physics contains many cases where they led somewhere real. The relationship between theoretical physics and experiment is not a simple hierarchy in which experiment is king and theory merely serves it. Theory sometimes runs ahead of experiment by decades. The existence of antimatter was predicted theoretically before it was observed. The existence of the Higgs boson was predicted theoretically 49 years before it was found. In these cases, theory was not serving experiment. Theory was telling experiment where to look. The relationship is more like a conversation between two people who have different but complementary access to the truth, and who need each other to avoid the particular errors that each is prone to making alone. What is true in physics is true in the transmission of physics. The conversation between the physicist and the public is a different kind of conversation than the one between theorist and experimentalist. But it is a conversation, not a broadcast. It goes wrong when it is treated as a broadcast. It goes wrong when the physicist assumes that what they need to do is transfer information from their head into the listener's head, efficiently and without friction. Information transfer is part of it, but it is not the most important part. The most important part is something harder to name. It is the transmission of a way of being curious. Not a specific set of facts, not a specific set of techniques, but a posture toward the world. The posture of someone who genuinely thinks the world is strange in interesting ways, who is genuinely interested in being wrong, who treats an anomaly not as a problem to be explained away, but as a clue to follow. This posture is contagious. It does not transfer through formal instruction. It transfers through contact with someone who has it. This is why the best science communication is not really about simplification. It is about invitation. The cathedral books invite you to feel the wonder without requiring you to go inside. The rarer books invite you to go inside, to actually handle the material, to discover that the material is harder than you expected and also more interesting than you expected. Both kinds of invitation are legitimate, but only the second kind produces physicists. The stakes of all of this are not merely academic. They become concrete when you consider what happens when governments decide to regulate the act of public scientific education. This is not a hypothetical. It has happened, it is happening, and the form it takes is instructive. It does not come, usually, as an explicit prohibition. It comes as a requirement. You must register. You must apply for permission. You must demonstrate that your activity meets certain criteria defined by certain people in certain offices, who have the authority to decide whether your explanation of quantum mechanics is acceptable or whether it requires adjustment. The criteria are vague. The vagueness is not an accident. Vague criteria can be applied flexibly, which means they can be applied to silence whatever needs to be silenced without creating the drama of an explicit ban. The effect of such requirements, even before they are applied, is to change the behavior of people who explain science. The rational response to a permission requirement is to avoid anything that might prompt the permission to be denied. This is called self-censorship, but the term is misleading. It suggests a deliberate choice, a conscious decision to stay quiet. In reality, it happens much earlier, at the level of what topics you choose to think about, what questions you choose to address, what implications you choose to follow. The self-censorship is invisible because it happens before anything visible occurs. The interesting thing about science, and specifically about physics, is that it has no natural stopping point. A question about how the GPS in your phone works leads naturally to a question about why time runs differently at different speeds, which leads naturally to a question about the structure of space-time, which leads naturally to a question about what existed before the universe, which leads naturally to a question about whether the word before applies in that context, which leads naturally to questions that physicists are currently fighting over. There is no clean line between physics and philosophy, or between physics and cosmology, or between physics and the kinds of questions that have always been most politically sensitive, questions about origins, about scale, about the relationship between the human and the fundamental. Any regulation of what physicists can explain in public is therefore, inevitably, a regulation that reaches into the heart of physics itself. You cannot regulate the explanation without eventually regulating what can be explained. And what can be explained is what people can think about. The chain is not immediate, but it is real. The universities that produced Feynman and Schwinger and Heisenberg and Bohr were not institutions where the range of permissible ideas was narrowed by external authority. They were, with all their human flaws and institutional limitations, places where the only check on an idea was whether it was true. The physicists who push back against such regulations are not being naive. They are not failing to understand the political realities. They understand the political realities very well, and they also understand something that politicians sometimes do not, that the instrument they are trying to protect, the free explanation of how the world works, addressed to as many people as possible, in as honest and rigorous a way as possible, is not a luxury that science produces after the important work is done. It is how the important work gets done. The culture of physics, the culture that produces the next generation of people who can do physics, is inseparable from the culture of free scientific communication. Restrict one and you damage the other. This damage may not show up for a decade. When it does, it is very difficult to reverse. The petition in this case was not primarily an act of resistance. It was an act of refusal, a refusal to pretend that the thing being regulated did not matter. It mattered. It matters in ways that are difficult to quantify and therefore easy to dismiss. The people doing the dismissing are often not malicious. They simply operate inside a framework where what cannot be quantified does not register. They see a regulation and they see efficiency. They do not see what the regulation would cost, because what it would cost is precisely the kind of thing that cannot be put in a column. One of the most important lessons from the sociology of science is that the things which look most robust, the established institutions, the well-funded research programs, the prestigious journals, the famous research groups, are often more fragile than they appear. They depend on conditions that took generations to create and can be disrupted in years. They depend on people choosing to enter a difficult field with uncertain rewards, because the questions are genuinely interesting. They depend on young researchers being willing to spend their most productive years on problems that may yield nothing. They depend on the transmission of intellectual culture from one generation to the next, which happens through contact between people and cannot be replaced by any institutional substitute. And all of this depends at the foundation on the public believing that physics is worth doing. Not that it is useful. Usefulness can be demonstrated by pointing at smartphones and satellite navigation. But that it is worth doing in the deeper sense, that understanding the universe is in itself a legitimate human project, that curiosity about fundamental questions is in itself a legitimate activity, that the investment of human genius in the study of things that have no immediate application is in itself worthwhile. This belief in the general public does not come from nothing. It is cultivated. It is cultivated by books and lectures and conversations and demonstrations and the accumulated efforts of thousands of people who believed that the world should understand what physics has found. The physicist who spends an afternoon explaining quantum mechanics to a group of engineering students is doing something that looks peripheral but is actually central. The science communicator who writes a script about the structure of the sun is doing something that looks like entertainment, but is actually infrastructure. The popular science author who spends 3 years writing a book for high school students who might become physicists is doing something that looks like a personal project, but is actually a piece of the chain along which the capacity to do physics passes from one generation to the next. None of this can be mandated. None of it can be regulated into existence. It can only be allowed to happen. Allowed by institutions, allowed by governments, allowed by the general willingness of society to accept that some of the most important human activities are also the ones least amenable to immediate measurement. The moment you begin measuring them in the wrong way, they stop happening. And once they stop, the reconstruction is not a matter of policy. It is a matter of time, generations of time, time during which the questions remain, but the capacity to answer them quietly disappears. So, what does a physics book actually do? Not the textbook, not the cathedral, but the rarer thing in between. It does something quietly extraordinary. It finds a person who is standing in the gap between wonder and understanding, between the feeling of knowledge and knowledge itself, and it builds very carefully a floor. Not the ceiling, not the answer. Just a floor, solid enough to stand on, high enough that you can see a little further than before. And from that floor, if the book has done its work, you can see that there is more above. Not vaguely more, specifically more, enough more that you know what you're missing. Enough more that the next step becomes thinkable. Most people never get this floor. They get wonder, and then they get a wall, and behind the wall, the physics keeps happening. The calculations, the arguments, the astonishing specific things that the universe turns out to be made of, and most people never know about it. This is not a tragedy, exactly. People live without this knowledge, and their lives are full and real and not diminished. But something is missing. A form of contact with reality is missing. A form of knowing where you are and how you got here and what kind of place this is missing. The books that try to provide this floor are maddening to write and sometimes maddening to read. They ask more of the reader than the cathedrals do. They give less, in some ways, than the technical literature does. They occupy an uncomfortable middle position, and they do not apologize for it, because the middle position is where a certain kind of reader lives, and that reader deserves something written specifically for them. The physicist who agrees to write such a book To translate 3 years of lectures into a text that demands the reader's full attention without demanding their graduate training is doing something that does not fit comfortably into any metric of academic productivity. It will not be cited in the journals that matter to the funding bodies. It will not produce a discovery. It will produce, if it works, a few hundred or a few thousand people who understand more than they did before, people who may or may not go on to do physics themselves, but who will in any case carry a more accurate picture of what physics is and what it is for. This may be the most important thing that physics can give to people who are not physicists. Not the specific results, not the structure of the proton or the geometry of spacetime, but the way of asking, the insistence that a feeling of understanding is not the same as understanding. The acceptance that the real answer is often stranger than any comfortable answer could be. The tolerance for the long middle of an investigation. The part where you do not know and cannot know yet whether you are getting anywhere. These are not just scientific virtues. They are, under almost any name you give them, exactly what clear thinking looks like. And clear thinking applied to the full range of questions that a person encounters in a life. Not just questions about physics, but questions about evidence and authority and probability and the appropriate response to uncertainty. Clear thinking is not a luxury. It is, in the conditions of the present world, something closer to a survival skill. The physicist at the blackboard, the science communicator in the studio, the author at the desk at 2 in the morning trying to find words for something that resists words. They are all doing versions of the same thing. They are trying to keep the channel open, to keep the connection alive between the way the universe actually works and the people who live in it. This is worth protecting. It is worth a petition. Worth an argument, worth the maddening work of translation from the language of mathematics into the language of the possible. Because the alternative, a world in which physics happens in silence, understood only by the people who do it, explained to everyone else only in the approved version, regulated into harmlessness by people who have confused their authority over the process with authority over the truth, this alternative is not neutral. It is a narrowing. And narrowing, once it begins, tends to continue. The questions are still there. The universe has not become less strange. Somewhere, a 12-year-old is picking up a thin paperback about the cosmos and feeling, for the first time, the weight of an enormous idea. What happens to that child, whether they find the next floor and the floor after that, whether they find someone who will tell them that their curiosity is not a hobby but a method, that the strangeness they feel is an accurate response to actual strangeness? This is not just their problem, it is ours.